Hi everyone, my name is Walter Carballosa from the Florida International University. I'm going to talk about the on-sum exponential topological indices on graph, and this is a joint work with Edil Molina from Autonomous University of Guerrero in Mexico, Autonomous Rodriguez from Universidad Carlos III de Madrid en España, y José María Cigarreta, también from the Autonomous University of Guerrero in Mexico, Acapulco, Guerrero. So, as you can see, I am going to talk about topological indices. In the case of topological indices, you have to understand that is a single number, just an expression that is going to provide a single number that represents a chemical structure in graph theoretical terms via the molecular graph, and that correlates with the molecular property. It is used to understand physical chemical property of chemical compounds. Topological indices has been studied widely, has been pretty interesting because they capture in a single number a lot of information about the property of the the behavior of the molecules in a single number. So there are several of the indices, and in special at the very beginning, a study from the seminar for Weiner. Um, but in order to provide you two important evidence, two example about the how useful and successful has been the topological indices, I'd have this example, for instance. So it's well known like there exists about 1,000 benzoyl hydrocarbons. So the known molecules of about 1,000 of benzoyl hydrocarbons. But that number is actually huge. For instance, the number of possible benzoyl hydrocarbon with 35 benzoyl rings is around five, a five, and number five followed by 21 zeros. So it's a huge number and a lot of them. So because of that, it makes sense if we are looking for some particular molecules with unexpected behavior or property, it makes sense to analyze which of the well-known or the new one topological index is pretty correlated, has a good correlation with the property, and do the research, analyze first what is which one is one that with a good result, and after that try to create or obtain in the lab or in practice. So this other example is just about that. In special, remember that when we are talking about the chemical graph, essentially we are talking about the maximum degree at most 4, and it's easy to manipulate or fix some kind of parameter in order to do optimization in those graphs. For instance, one of the examples, the successful example is that the connectivity index sheet 2 has showed good predicting ability in comparison with the benchmark set of other predictors. For example, its correlation coefficient with respect to the enthalpy of vaporization is equal to the 88.1%. So it's a high percentage, and we have another example with even above above 90%. So only two examples in order to show the successful of the use of the indices. In particular, we are going to work with in this work with uh, topological indices that are based on n vertex degree. That means we have an expression that depends on the degree of the two endpoint, and we are going to consider the sum, or some other spaces. In, so, in some other cases, could be the product of a symmetry expression that depend of the degree of the two endpoint of each edge. In particular, the rounded connectivity index is one of the one very well-known of those indices. We have the extension obtained by Goldman through NAFTA. There is a first and second segway indices. We also have some others just to mention the specials, the ones that we are going to use in this talk. Pratt index, defined like up here in the first equation. AVC index, that is atom bounds connectivity index, and the some connectivity indices. These are some examples that are easy to stem, generalize. In the special, one of the ways to generalize the topological indices is using the parameter. And there are words using the parameters in order to test or verify the, um, the correlation of one particular family, of those parameter with respect to a particular property. This is our example that we are going to use in this work. There are the generalized second sacred index, the generalized sun connectivity index, and the generalized atom bounds connectivity index. In this case, we are talking about the parameter alpha, that is a real parameter. Eventually, for some definition, could be positive or non-zero, depending on the particular extension. So in our world, we are going to focus with exponential. What is the idea of the exponential? When we have an index that is based in its computation in the sum of terms that are associated to the symmetry function with two input, double input, to the degree of the two component of each age, we can instantaneously obtain the exponential. Of course, exponential by obvious reason is the sum of e to the expression, the output of the function, instead of the direct sum of the function. So this is exponential. We have this is for whatever general symmetry function. And this is in this work that we are going to do is obtaining equality related general exponential indices of the graph that directly deal with new inequalities involving some well-known topological indices like the generalized atom bounds connectivity index. ABC alpha is corresponding exponential. The second sub-rate index is corresponding exponential index, and some others. As usual, we are going to start with two lemmas that are basically the most important to technical results that we are going to use. This is a direct consequence of Janssen, sorry, in order to talk about the the exponential indices. Notice that, so as I told you, if we have, let G be a graph with psi m, maximum and minimum degree, uppercase delta and lowercase delta respectively, and f satisfied that is a bound, lower bound A, upper bound B for every xy double input in the range of the minimum degree and maximum degree as expected in the graph, then we are going to obtain basic and clear direct bounds for the exponential and also a direct relation using Jensen inequality with exponential index associated to f and the index associated to f. So the important thing is that because of the application of Janssen and the trivial algebra used and a couple of details, we are going to obtain the inequality in the lower bounds into an upper bound into directly followed by the output of the function of this maximum or hold the maximum or hold the minimum. And in the equation number 3, the equality is obtained at holds if and only if all the atoms in the sun are the same. Another technical result is this that establishes a relation between two functions. So consider two symmetry functions f1 and f2, define the corresponding index capital F1, capital F2, and consider these constraints. The relation between both associate with an inequality involving coefficient, one coefficient constants, coefficient C. That is going to be a typical and very used in practice and very general as well. So under this consideration, we are going to working with a general function. We are going to obtain this inequality due to Jensen and also the monotony of of the function, the exponential function. So, and the tide is going to be obtained just in the case if and only if there exists a constant case such that for whatever age UV, the output of the corresponding F1 and F2 are proportional. All of them are equal for, for F2 and all of them are equal for F1 as well. So, in order to obtain result using DSS2 lemmas and some other results, technical results, a few of them, we have this new theorem. Notice that the theorem establishes a relation upper bound and lower bound for the exponential generalized atom bounds connectivity index and the fact that depend of the maximum degree only depend on the maximum degree separate by when alpha is positive, when alpha is negative, and n1 is the number of isolated edges. When alpha is negative, it's required to consider that not isolated edges appear. And a couple of consideration about that. In the case of the maximum degree is equal to 2, this is true for whatever graph that verify the condition. When the maximum degree is strictly greater than 2, the lower bound in 1 is obtained by disjoint union of regular graph and whatever number of isolate edges, and the upper bound is holds if and only if G is a disjoint union of star graph with maximum degree delta. And of course, whatever number of isolate edges. If delta is greater than 2, the equality of the lower bound for 2 is obtained if and only if is a disjoint union of a star graph with maximum degree delta, capital delta, and the inequality of the upper bound is obtained if and only if D is a regular graph. So we have minimum and maximum for atom bonds connectivity. These are the result also working with exponential generalized atom bounds connectivity indices, but incorporate the fact of the minimum degree strictly greater than 1. Remember that if delta is equal to 1, it's the same thing for every at n. So if it's in that case, we have that it result a bound that depend on maximum and minimum degree for when alpha is greater than 0, when the minimum degree is greater than 2, we are able to determine that the tide holds if and only if G is a disjoint union of regular graph, and of course, whatever number of isolated edges. If we consider not isolated edges and alpha and negative values of alpha, we are going to obtain similar result, of course, because of the negative, the monotonicity, associated to the negative alpha. We obtain similar result, but usually in the opposite bounds, And when delta is greater than 2, the inequality holds if and only if G is a regular graph. That is usually one of the typical maximum. So for the atom or the atom bounds, generalized atom bounds connectivity, we have a relation between a direct relation between the exponential and the AVC alpha, and the tide hold if and only if G is in G all the edges are incident to a vector of degree 2, or G is regular, or G is biregular. By biregular, in this case, we are going to consider a bipartite graph where each part is exactly the vertex with the same degree. And this result improves the result present by Das at L in discrete applied mathematics this current years, 2021. Notice that is exactly this term over here that is improved, the one that is improved. Another relation that we are able to obtain with this is two is using the ABC alpha and the exponential generalized ABC and the second set rate, generalized second set rate. In order to provide a general idea about this, select properly an F1, an F2, and obtain a bound for C that works for C, and obtain this is a relation with the separate cases. When delta, the minimum degree is greater than or equal to 2, when the minimum degree is equal to 1, and some isolate allows some isolate the edges, we obtain this as inequality or relation between the corresponding exponential generalized ABC alpha and M2 alpha with information about the tide when the tide is appear or occur. Something similar, we are able to obtain a relation between the atom of ABC alpha, the exponential, and the corresponding exponential of the Pratt, the analyzed Pratt. Similar procedure with different difficulty, but a little of algebra and modification, just selecting the proper constancy and the function f1 and f2. Notice that over here we are able to obtain both lower bound and upper bound of each other. The final result, that's something that is important, is that obtain results associated to the ABC alpha, the exponential of the ABC alpha, but comparing two different values of alpha and beta, like you see over here. Notice that this is interesting because provide direct bounds and could be useful in order to select what is step by step in the experimental or statistical analysis of the testing of correlation between the generalized index and the corresponding property. So I think I tried to complete on time. This is the presentation, and I am ready for you for any question that you still have. Thank you.